All right, preamble, I guess, before we start going today, some videos. We're talking about fluid dynamics, so the fact that they're moving and impinging on things. And so this isn't so different if the guy was flat on his face with the jetpack going horizontally. It's not so different from blowing the truck off the apron at SFO. So the same idea. So you convert chemical energy, I presume, in this case, by burning something into an expanded jet, just like a jet engine, and it gets forced out, and it lifts, elevates you, or pushes you along, depending on which way you're oriented, and it acts in the opposite direction of the nozzle. It starts off with a high velocity as it comes out, and when it impinges something, which is the ground in this particular case, it provides enough of a reaction that's able to lift you off and scoot you around. So that's one. What else have we got? Not sure. Oh yeah, this is just a bit of fun, because we'll do an example like this using Bernoulli. And so this is a different one. I don't know. I think it's the falls in Brazil. I remember in 1990, I guess it was 1990, because our first daughter had just been born, went to work in Canada for a summer to teach a short course. And Jesse, I can't remember his last name, kayaked over the falls. That's not this guy. His battered kayak was found. His body was never found. And I guess this isn't Niagara Falls, but this is a different falls, I think in Brazil, with a guy, and I don't know whether he survived or not. But we'll do an example like this. And actually, him going over the falls with the water is just like he'll be traveling at exactly the same speed as the water. So that's a good illustration in that regard, in that all we're doing in fluid mechanics is taking a packet of water. It could be a packet of water in a balloon, or it could be something solid, but it performs directly the same as the weights that you would throw around in your statics course. You do take 212, right? Yeah, it must do. In dynamics, I guess, is what we're doing. So I remember that. What else have we got? First barrel, right? People go down barrels and survive. The barrel will be going down just as if you've dropped it off a 10-story building, I guess. Niagara Falls is 100-some feet, 10 feet for a story, and therefore a 10-story building. And so, but people do survive, and I guess you need to have enough cushioning inside that to make sure that when you decelerate, you don't decelerate instantly. Hitting water is pretty hard, I think, right? That's why as you walk across the Golden Gate Bridge, there's a telephone in the middle for people who aren't so happy and want to jump. They don't die from drowning, they die because of the impact. Is the same as jumping, almost the same as jumping onto a concrete ground. Water is quite incompressible at very high rates. It doesn't deform to get out of the way. It does if you're 30 feet on a diving board, but otherwise it doesn't. And so all the things that we'll talk about Bernoulli are in those things: linear behavior, falling down, going horizontally, the jet pack as well. But today we'll add to our repertoire and we'll look at pressures as you go from one parallel streamline to another, and use that to calculate what the pressure change would be for that. And so the best example of centripetal force is looking at this idea here. It's the same as a fairground ride where you go down a water park slide. You use centripetal force to anchor you to the floor, the road in this particular case, or the wall if you're going down a water slide. And we can derive some expressions for that. And I think there's one more video left that does that. That's this. 42 seconds. No sound. You get to listen to me instead. But the same idea is a car driving on a loop-the-loop, the Jaguar. This is water in a loop-the-loop. And this looks like quite an amazing setup with a vertical drop into a curve and then going around. I don't know exactly what this doesn't look like what is it, Sandusky Point or Six Flags, I guess. Perhaps it's an experimental one. I don't know exactly what it is, but it's the same idea. You have start off here, you convert your potential energy Z with V being 0, no velocity. And whoops. And you convert all the different states of energy as you go down. So actually it's perhaps worthwhile talking about that. So I won't go into that. So that's what we'll talk about today. Any other things before we get going? You know your stuff is on Monday. Great. You'll be able to show exactly everything, that you know everything about this class. I'll be around today if people want to chat. Questions? 30 minutes, probably on the tables by 7:55. Fine. I think I'll come tomorrow, Monday, along with Junpeng, and do it. So you've seen all the stuff in the videos. Fine to take a photograph of your script after you've done it. The solution is posted usually a couple of hours after, because everyone will do it at the same time. Okay, great. Happy hunting. I'll wish you well again before we part today. Fine. Okay. All right. This is useful, right? So I made the point. I looked on my shelf today before I came out. Do I have a little cube that I could use to make an illustrative point? I saw a Rubik's cube, but I was too lazy to bring that. And it sits inside a little box, a little sake box, which was given me by a Japanese colleague, which is a small box made of pine wood, which apparently when you join two tunnels together in construction, you celebrate it. And traditional way is to drink out of this little box. So I was happily reminded by that. But this example we did says it all. That we talk about linear Bernoulli in terms of elevation head, pressure head, and velocity head. And you can think of this as a reverse of this. This has a big elevation head, Z, but the pressure is atmospheric, and it has no velocity. If I drop it, then as it comes down, when it gets close to the floor, the velocity is large, Z is small, and so it's traded kinetic energy for potential energy, switch one from the other, and pressure is still nothing. And then when it hits the ground, 1 minute after it was going very fast, it destroys that velocity and converts it into a force, the pressure. So that's the process working in the opposite way here, and that was the process that was working in the direction for the 747 sitting at SFO. Velocity coming out of the back of the jet, zero pressure outside the jet, hits maximum velocity before it hits the truck, and then as it hits the truck, there's what we call the stagnation point. It stops, V is zero, it transfers that velocity, V squared, half mv squared, it's V squared over 2g in our Bernoulli term, and it converts it into the pressure that's applied on the truck, and we can take moments around something to be able to show that it gets moved. Okay, right. So that's where we are. So think of water as a little cube of something that's moving along that happens to be able to link together. What we made the point, I guess, that we could have. This is my chance to draw an airfoil. And we have similar behaviors here. If we do this, you kind of know, I think you probably know how an airfoil on a plane works. Converts it into a straight line if I'm not careful. And you could imagine that there'd be a whole bunch of these are streamlines, what we refer to as streamlines. And of course, they're the line at which a particle would travel. And we can define a coordinate system on these, which is important to us, which is normal to it and in the direction of it. This is the streamline velocity. This is the normal velocity, if you like. And when we do evaluations between 2 points, we said that we talk about an upstream and a downstream. Actually, we don't have to write them upstream or downstream. We could write it downstream to upstream because we said it's for inviscid fluids, no viscosity, so there's no energy loss in it. And you get exactly the same answer if you wrote it from 2 to 1 as you would from 1 to 2. You wouldn't if you did it when we start including viscosity. And And so these are streamlines, and I guess you can think of this also as being a stream tube. And so I guess I can do it here. I'm going to erase that other one that I put in before. So the stream tube would be something that exists between two streamlines. And we'll play around with that later, not today. So we also said that this expression here is mass times acceleration in the streamline direction. I'm going to put minus, and I'm going to call this force 1, and I'm going to call this force 2 equals 0. So in other words, I'm writing F equals MA streamline, which I can also write as F minus MA equals 0. Sum of all the forces, so there are two here. And they apply to each of these terms. This v squared term is for our acceleration. It represents the fact that we're interested in what the acceleration is, not that I feel that I'm going at dv dt and it changes with location. It converts that dv dt in time attached to me to a dv dx in space, because we're going between points 1 and 2. And so this v squared term is just this acceleration, because you know that we wrote acceleration in the streamline is change in velocity with time, but it's also change in velocity multiplied by 1, which is dv dx times v. So dv dx dt is, this term is just a velocity, right? This term here. Don't need to derive these, just have to, it's good to get a feel for what we're talking about. All we're doing is converting acceleration between points, how the fluid accelerates from point 1 to point 2. We're not writing it attached to the piece of fluid that's traveling, but we're attaching it just by knowing what the velocities are at each of these points. And it becomes this v squared term. If we integrate this, we get Bernoulli's equation. I prefer to write this as P over gamma plus v squared over 2g. Don't know why it won't write. Plus z equals constant. And we've done some examples for this using exactly this. So you write it at point 1 and point 2. You have 6 terms in 2 equations that you can equate to each other, and you hope you only have one unknown. On the apron at San Francisco Airport, the only unknown was the pressure that we get converted from the velocity coming out of the plane, 100 miles an hour, 200 meters a second, that we change from 200 meters a second to 0, and we calculate the pressure that is developed. So in other words, we wrote this as P2 over gamma plus V2 squared over 2G plus Z2. These were all point ones. And the only term that we have that we don't know is this. And so we can work with that. So that's what we do. So today we're going to, perhaps we'll do another example along those lines, but I want to talk about centripetal acceleration. So the jag going around the thing. So you could, I don't know, I can't do it. I can't do it. Can't see the screen anymore. If I twirl something around my head, you know that the weight on the end of this thing is pulling out, and it's being restrained because it's exerting a tension on this wire, which is keeping it in place. even if I rotate it at constant rate, so I don't know, a revolution a second or whatever, then this end is going at the same speed, but not the same velocity. Velocity has both a magnitude, 1 meter a second, but also direction. And this is going parallel to this bench here, and it's going perpendicular to the bench here, parallel and perpendicular. So it's switching through a whole series of angles as it goes across the room. And so it has an acceleration. So the velocity is changing, the speed is constant, but the direction is changing as it goes around. And so I guess, will I do this? Yeah, I can do this. So, oh, is it back on? I saw it light up in the side. So you can imagine that this is here. And so this angle here is theta. This angle here, this is r, a radius. This is a radius outwards, which could be lowercase r. And I guess at this point here, r is equal to uppercase R, in this particular case. And this is r equals 0. And this is my little weight that I have, which is my packet of water, which is spinning around. Yeah, don't need anything else. So in years past, I've done a derivation, but I don't want to do that today. I'll save you that. And so what I will do, though, is I will take the expression that we have here, and I'll sequester it from this, and I'll write this. And that is that this is sum of forces minus and I will do this. So that's quite apparent, I think, right? If I draw a line down through here. So this is the angular acceleration term, changing direction. It's being spun around at a radius r. It has some density. I guess I could have done this, that if I divide these through by, if I divide this through by a volume, and if I divide this through by a volume, you can't see that very well, but mass divided by volume is a density. So this is a density. So that's why this turns up in this constant here. But so it's a force per unit volume of fluid. Now, too much information. And so this is an angular acceleration. And if I get this right, this is angular acceleration is equal to v theta squared over the radius that which it goes through. So that'd be uppercase R in this particular case, just the definition of this term. And so if you make some substitutions and you play around with it, you get this term in its differential form. And if you integrate it, as we did, this was a differential form, we integrated it to get Bernoulli. This just means that if you're dealing with a compressible gas and the density changes with pressure, you can accommodate this. You can just get rid of this integration and just report this as P over rho in all cases where it's incompressible. Likewise, that's the case here. And so the standard result that we'll use is going to be this magnitude here. And so let's do an example that uses this equation. You could derive it just by using F equals ma and using the equation for velocity and manipulating this, that, and the other, but why not? Why do that? We don't need pain today. This is how good I am. I'm saving you all of this. And we'll do an example. And so I wonder if I can grab this. I tried this last time, right, to grab it, and it didn't work, but let me see. I can draw it out if I can't grab it. I fear that I can't. And if I can't, oh, so now you'll have to catch up. Sorry. I want to move it to where I want to move it. No, perhaps I'll move it here. Then, yeah, good. So, draw yourself a figure. Can I make it bigger? I'm going to get an A for cartography today, or draftsmanship. So this is exactly the idea. So you can imagine if instead of this being water, you're driving down a road and you are going horizontally, at whatever velocity, you'll feel like you're sitting in your car, you'll see no change. You know that when you go over a blind hill or a crest, that you'll get lifted out of your seat, and so you'll feel less than g. And you know that if you drive into a dip, you'd see the opposite. And so you can imagine that's the same as starting up in an elevator. As you go up, it's the same as being driven into your seat because you're pushing up against gravity as you go into the hollow. And this is being the opposite, that this is dropping down. And so we can think about that in the same way as we've done before. So what we're going to do is we're going to take this, and I'm going to divide it between these two locations, and we're going to write our expression in terms of this. And so on the left-hand side, so what I'm interested in doing is I'm interested not in going from 1 to 3, which would be along a streamline, for which we'd use this top equation. I'm interested in going from 1 to 2, and then from independently going from 3 to 4. And so if I go from 1 to 2, I want to use this equation. So this gives me P over rho. No, it doesn't. It gives me P plus rho integral V squared over uppercase R plus gamma Z. Is that right? Okay. Oh, missed out the dn. Instead of erasing it, you can put it in. Just hot today. And that is equal to P plus rho integral V squared over R dn plus gamma Z. I want to make another portion on this, and I'm going to add to the annotation above it. And that annotation above it will be that this is Z. And in addition to this, this is n hat. N hat is a normal vector that's acting directly into the center of rotation here, which is this term here. And so in this particular case, if Z is acting upwards and N is acting downwards, then dn is equal to minus dz. Oops, sorry. Is my writing legible? Am I talking loud enough? Legible? Fine. So if z is upwards and this is pointing downwards, they're the vector opposites of each other. So each single component of this has a minus component of this. So you know that for your math. And so for each of these, let's write Bernoulli from 1 to 1 to 1 to 2 to 2 to 2. The velocity in this particular case is in this direction, v. So v2 and v1 will be largely the same. And so let's try and figure out what p1 would be as a function of the other components. It's, well, first of all, what is R for these ones? I don't want you to score over your drawing, but the radius of this particular system would be only, I'm going to erase these, only if this radius is equal to infinity, right? These lines are parallel. So to get two parallel circles, you have to have an infinite radius of curvature. And so the radius of curvature here has to be infinite. And so if for these R equals infinity, then that means that this goes to, this is infinity, so it drops out. And this is infinity, so this drops out. And so you're left with just these terms, which are P1 is equal to P2 plus unit weight of Z2 minus Z1. If Z2 minus Z1 is what we call H, then this is just equal to H. And so this exactly is saying that if we want to calculate the pressure at point 1 from point 2, we know that the pressure at point 2, if it's a free surface, is atmospheric. And so to get this, this would be our pressure distribution. We could do this with space. Nothing you haven't seen before. It's exactly what you've seen before. It's a linear varying pressure. You could choose one to be anywhere closer to 2 or lower down for that matter. You'd keep on going. And so the distribution at this point, which is at H, is just going to be gamma H. So that's all this says. Great. So we spent half an hour to do something not very useful. It just says that even if the fluid's moving, if it's not accelerating, which it isn't accelerating laterally because it's not speeding up as you go downstream, and it's not speeding angularly because it's not going around a corner, then the static fluid is just the same as being in a box and being moved across the room, not accelerated across the room. Okay, we can do the same for the other one. Let's be color consistent. Bless you. Let's write it again. P plus rho integral V squared over uppercase R dn plus gamma Z plus, it'd be exactly the same, not plus, equals P plus rho integral V squared over R dn plus how do I write it? Gamma Z. Same as before, but not 1 and 2. It's between 3 and 4. And so we can rearrange that now in terms of, we'd like to know what P3 is as a function of P4. So let's arrange it in terms of P3. P3 is equal to, no one pointing out my idiot errors? What number should go there? Thank you. Four. And so this would be P4 plus unit weight of fluid, Z4 minus Z3. Whoops. And just as before, this term is equal to H. And plus rho integral V 4 squared over R dn, kind of a long one, minus integral, well, that's a bit poor, V3 over R. There's a rho in there, and there's a dn. Okay, agree with that, hopefully? So what are we going to do now? what we're going to do is we're going to realize that this is dz, but this is dn. So again, for these, we can come up with dn is equal to minus dz. And so we can rewrite this as, well, I'm not going to rewrite the whole thing. The only term that we're going to have to worry about, which is different from the before, is these are exactly the same as before. This will be atmospheric pressure because it's on a free surface sitting up here. And so we have to figure out exactly what this is. So this integration is between 0 and R4. And this is between 0 and R3. This is 0. This would be, call it uppercase R3. And this total one would be to R4. And we also made the point that this is true. So we could replace dn. Well, let's not do that yet. Let's do this first. So we can rewrite this as P3 is equal to 0 plus unit weight times h plus, you know that you can write the integral for this if this was n and this was a function of n, that this was something like this. This is 0, this is n1, sorry, this is n3, and this is n4. So if you do the integration from 0 to 4, which is this total area here, and you subtract from that the integration from 0 to R3, which is this, then you're left with the integration is actually just this portion here. Oops, I wanted this one. I love this filler here. It's just this thing here. So we can write this integration as you well know. You could write this as equal to density times the integral 0 to 4 minus 0 to 3, just gives a lower limit of R3 to R4. And it's V. Let's also write the fact that V4 is about equal to V3. It's not, it's going to be perhaps faster for V4, right? Because it has to catch up because it's going along a bigger arc, but let's assume that they're the same. And so we can write this as just V squared over R dn. And if I now write it as P3 is equal to 0 plus the unit weight times the depth minus, if I substitute dz for this, minus dz, then it's rho integral R3 minus R2, 4, V squared over R. Looks complicated, but really all it is saying that if you plot V and you measure that V at R3 and R4, and I guess V would vary in some small amount as you go along here, right? Because it's going along a bigger arc, so to keep up with the fluids that are around it, just like going on the top of an airfoil like the bottom, they kind of have to join up at the end, and that's why it's going faster on the top and slower on the bottom, because it's a longer distance. That's the same here. But so it would vary a little bit as you go in length, but this integral that we're talking about is if this was V squared, then this integral would just be this volume. That's what an integral means, right? So it looks kind of complicated, but it's just the sum of all the velocities between R3 and R4 over that patch. And so I'm not going to calculate what those are, but I'll make the point that in this, velocity is positive, and even if it wasn't positive, actually we talked about the coordinate system. This is our x, y, z for our rude right-handed coordinate system. For our rotational coordinate system, this is z, and the rotation direction is in the direction of my fingers. So this would be counterclockwise looking down on it. Don't have to worry about it. You get exactly the same results if you're going this way or this way. But the point here is that this is always positive. Velocity, even if it was in the opposite direction, is going to be squared. It's always positive. Radius is always positive, and this is positive between these two locations here. Radius is a radius, but if we're oriented in the vertical direction, radius is also the same as z. And so the punchline of this is that this term has to be a positive term, and so P3 is equal to 0 plus the static pressure as you go down in depth. So as if I draw it here, let me draw it in this way because we've always done it this way, right? This is pressure. If this is pressure and this is depth, pressure with depth, then this is minus a small constant. It's not a material constant, but this expression gives you a single value, which is this. And so it means that the actual value of the pressure as you go down is not this, but is something slightly less than this, right? It's going to be the blue curve rather than this. And it's going to be sensibly linearly varying as you go down from 0 here to some. So this will be the delta P that it changes as it goes down, this length here. So that's it. And so don't need to do the math, but just understand the concept and the fact that it makes sense. You go over a curve in a car, you feel coming out of the seat. That's because you're feeling less gravity. It's the same as if you start an elevator going downwards, it drops out from underneath you. It goes at the speed, accelerates below you at the speed of gravity. So acceleration in the z direction is minus g, because it's downwards. Then you'd be weightless. And so you feel less pressure as you go down. Okay? If you do it in the other direction, okay, everyone good with that? What happens if you do it in the other direction? What happens if you're flowing along? Whoops, not very good one. What happens if you're doing this? I'm getting good. But let's say that this time you have the stuff below you. I'm going to use the same terminology as before. So this is going to be 4 and 3. I guess we'd want to now, we'd now want to be able to, I guess it'd be the same, right? And so what would we have? I can make my life easier by taking, doesn't do it if I do it with a pen, but it does it if I do this. So this is what we had before. I'm going to erase some of these and see what happens. Well, I wish I could reset this back so it doesn't turn off the eraser every time I pick up the pen. Whoops. Control Z brings it back, I guess. Bear with me. All right. So how does that rationalize? I guess the other thing we should also note is that in this particular case, this is R. This is N. And this is Z. So now dN is equal to dz. Right? They're both acting in the same direction. We swapped out dN for minus dz before, and as a consequence of that, we got this term here. And so now what we need to do is we need to add this, and we need to add this. And so now, without going through tons of math again, you know that when you go through a hollow and you come up through a dip, you get pushed into your seat. So now the pressure at P3 would be just the linear distribution with depth, which would be, if I do this, this is pressure, P. This is the free surface, atmospheric. Feels exactly what we're feeling. As you go down a distance h, you would measure unit weight times h. And if you are going through this thing, this would be the amount, if you can see this, this is delta P, which is this, which we've added. And so that's just a rationalization of this. Okay. So, interesting. By far, we'll use linear Bernoulli 9 times out of 10, but we can use it to go across boundaries to be able to see how pressure changes away from it. Not so useful, really. If you want to know what the pressure is on the top of the wing, you just need to know it at this point versus this point, and you get that from the along streamline velocities, along streamline Bernoulli. And so, but it has some application. The other thing I guess you can do is you could look at the fun ride. And so the fun ride is if you turn this system upside down, Control Z. Okay. So these are the two things. So this is the Jaguar with its wheels on the base. And so you can do the same thing here. And I did it. And you'd have to write 3 and 4. And you can write it, I think, the same as before. P3 minus, yeah, okay, do this. So I can take this expression here. So I can take P3 I have to include P4 now, is equal to, I can subtract this off, which is gamma H, and I can subtract this off, which is rho integral V squared over R dz, and I can set this equal to P4. This was P4 here, right? We got rid of it. And so now, if we want to look at the pressures that are present here, then, well, I won't draw that in first. We want to calculate P4. We know that P3 is equal to 0. We know that as we go upwards, an amount h, which is a different distance between these streamlines. This is just h between 3 and 4. Then we're going from 0 here upwards. So I guess the pressure distribution would be like this. And it would be getting less. And the only way that it would be positive if the magnitude of the rotation, this is going to change back to the previous magnitude because z is upwards and n is inwards, right? So this is z, but this is n. And so this term changes over. Take it on trust. And so it means that to be able to be held on the wall of death, what you already know, car's got to be going fast enough so it doesn't fall off. If it's going too slow, it'll just drop down on its hood, on its roof. And I guess the other thing that you could do is you could think of it like this. This is your packet of car. This is the weight of car. And this is the force that's acting downwards. And so if you calculate I guess we'll call this F theta, not this, then this is just Newton's law. This is F8 equals m a theta, which is equal to m r omega, let's write it, e squared over r squared. And if you equate this with mg, e squared, so this is just, these are equal to each other. mr v squared over mr v squared over r squared. Then you end up with and so you get out of it the fact, I guess we can get rid of one of these. You get that v squared is equal to gr. And so you can calculate the velocity that you have to go depending on the planet you're on and also the radius by which you go through it. And so a smaller radius means a smaller velocity, which makes sense, right? If it's a tighter turn. If it's a really shallow turn, you'd have to be going really quickly to be able to keep, because you're just going, in the limit, you'd be going horizontally as r goes to infinity. And you know that if r goes to infinity and you're going horizontally, you just drop down. So this would be the required velocity, the required speed that you'd need to go in an arc to be able to stop the car from falling down. Okay, so I don't know if that's confusing or not, but it all fits together. So the same kinds of things that gets a car around the track are the same mechanisms by which fluid goes around a track. And it really just comes down to Newton's second law, written in rotational coordinates for centrifugal acceleration. It gives you this term here that replaces the inertial term. And if we play around with it, we can do some interesting things to be able to see how pressures change. We know how pressures change as you go over a bump. They should reduce just because you come out of the seat in your car. If you go through the reverse, you get pushed into your seat, so the pressures should increase with depth as you go down. And this seems to kind of be contradictory with the idea that as you go around a curve, you're kind of pushed, you'd be pushed into your seat upwards, right? In this case, you'd be upside down. And that seems kind of contradictory with this idea here, but it's not, because your boundary conditions have changed. The boundary condition is that this is the free surface now instead of this. And so as you go from this free surface, the pressures would decrease as you go away from this location, as you go in the fluid. Okay. That's it. Yes?
So in this case, would it be similar to like one of those rides where you're basically stuck up against the wall as it...
The wall of death. Yes. And they take the floor out from underneath you. Has anyone ever been on those? I've seen them, never done it. Yeah. Well, you survived. Apparently you're here. Okay. So, as I say, 9 times out of 10 will use linear behavior. So, well, happy hunting on Monday, Wednesday, and Friday. Be smart. Take what I've said to heart. Verbatim tests, numbers changed. You know what the topics are. No notes, no books, but you'll be given exactly the same equation sheet that you have. And you can photograph your test so you know what your answers were, and the answers will be posted a couple of hours later. Good luck. Happy to see your excellence when you report it.